is to predict the relative strength of a resulting compound using Coulomb's law. And easily stated, ionic attractions of opposite charges is a very strong electrostatic bond. Very strong bonds. So electrons that are transferred until the metal loses all its valence electrons, and the nonmetal is going to gain until it fills its octet. So for example, if I see oxygen combining with lithium, oxygen who lives in group 6A, we placed 6 dots around it. Lithium who lives in group 1A only gets 1 dot around it. I can clearly see 2 lithiums needed to fill the octet around the oxygen. If 2 lithiums, each with 1 electron, are needed to satisfy the oxygen's octet, oxygen gain 2 becomes a -2, lithium loses 1 becomes a +1. We talked about the crisscross method. I can clearly see why it takes 2 lithiums to satisfy the 1 oxygen. Li2O is the name of this ionic compound. It would be called lithium oxide, a binary ionic compound. Very easy to use the periodic table when predicting the formulas. Predict the formula of a compound that forms between calcium and chlorine. Friends, we've gotten so good at this, I'm not sure we even need to draw the dot symbols to predict. We've got the charges written right on our periodic table. We took the time to do that last quarter. If I look at calcium, it lives in group 2A. I can see that it has 2 valence electrons and therefore will carry a +2 charge when it loses those. Chlorine lives in group 7A. There's 7 valence electrons, room to gain 1 more. If it gains 1 electron, it will carry a -1 charge. When calcium hooks to chloride, I crisscross charges. I can see the formula developing for calcium chloride is CaCl2. 1 electron from the calcium fills that chlorine. The other goes to the second chlorine. 2 chlorines now, each carrying a -1 because it's gained an electron. The +2 calcium with no dots around it because it's lost both of its electrons creates an ionic compound because of electron transfer with the name calcium chloride. So this is a review of how we crisscross charges and come up with formulas. Suppose in this example we have a metal, I'll call it M, has 2 valence electrons. It's going to hook with a nonmetal we'll call X, and it has 5 valence electrons. Why did I draw 6? Whoops, it has 5 valence electrons. If the metal loses both electrons, it's going to carry a +2 charge. If the nonmetal has 5, it needs to gain 3 to get 8. Crisscross your charges. We get M3X2. A total of 6 electrons were transferred to create this compound. I cannot name it because these were imaginary symbols. M3X2, although I know it would end in "-ide", whatever X was standing for. Consider charges to develop the formula. In covalent bonding, we imply that there is another way atoms can achieve the octet, and that's by sharing electrons in what's called a covalent bond. Literally, the nonmetals group together and share their outer electrons so that everyone achieves an octet. Electrons that are shared are called bonding pairs. Electrons that are not shared are called lone pairs or non-bonding pairs. That tends to be what I say, non-bonding electrons. Shared pairs are often represented by a solid line, and if I see 2 shared pairs, we'll often see that represented with a double line representing the double bond. This molecule kind of cleaned up would show oxygen has 1 lone pair, also called a non-bonding pair. It has a double bond to an oxygen that has 2 lone pairs, and then a single bond to the other oxygen with 3 sets of lone pairs. Sulfur is the central atom, a double bond off to one oxygen and a single bond off to the other. Just taking this picture into a more familiar format from last quarter. When 2 atoms share 1 pair of electrons, we called it a single covalent bond. One atom may use more than a single bond to fill its octet, but we usually call that the hydrogen duet rule. So here's what it looks like. If this is a fluorine atom separate from this fluorine atom, I can clearly see them separated. Each one has 7 valence electrons. Take this, however, and literally overlap the orbitals so that these 2 electrons become a shared pair. And when I count now, both electrons have an octet. Both of those nuclei have an octet. This shared pair of electrons is often represented by a single bond line. Same idea for water. Here's water, oxygen in the center with 6 dots around it. Each of the hydrogen has 1 valence electrons. Overlap those orbitals, and then those shared pairs around the oxygen count for 8. Hydrogen, who only needs to become like helium, has the pair it needs. 2 single covalent bonds, 2 lone pairs of electrons on the central atom of oxygen. Sometimes we have double covalent bonds, 2 shared pairs. If 2 sets of electrons overlap and share, we'll see that represented by 2 lines representing a double bond. Double covalent bonds are 4 electrons, 2 shared pairs. And of course, we know about the triple bond, as in a nitrogen molecule. Triple bonds represent 6 electrons or 3 shared pairs. Nitrogen molecule has 1, 2, 3 shared pairs or a triple bond, so that each one of the nitrogens ends up with the octet, the 8 that it so desires in its outer shell. Remember, hydrogen is much more stable if it only shares 1 pair to become like helium. So hydrogen does not obey the octet rule. Hydrogen only needs 2 electrons to fill its shell. Hydrogen needs to be like helium, its noble gas in the period 1. So when hydrogen combines with itself, we have a shared pair. When hydrogen combines with someone else, I usually think of it as plugging a hole. Here's a hole in the chlorine's octet. Place the hydrogen in. Hydrogen has 2, chlorine has 8. I always leave the hydrogens last when I'm building and kind of place them into an area that needs to have a partner. And the next slides are going to just show example after example that we worked last quarter. Hopefully this will come back to you. As we start building a water molecule, I see an empty spot on the oxygen here, an empty spot here. We can see literally how they come together to form a stable water. If oxygen has 6, this has 6, we pair them